Okay, now we're going to start a unit on electromagnetism and the relationship between current in a conductor and the magnetic field around the conductor was a real game changer. It made a lot of what we do today very possible. So this is a very exciting lesson. I'm excited to teach it. I hope you're excited to learn about it. Let's go to the presentation and study electromagnetism. Okay, here we are at the presentation for electromagnetism, and I'm going to do this in two parts. This is part one, which will focus on a DC or direct current electromagnet. So here on the screen I have a current carrying conductor, and let's say that I have current flowing in this direction. We're going to look at this gentleman here, Hans Christian Oersted. He was the scientist that discovered the link between electrical current and magnetic fields. And he was setting up for a demonstration, and when he was energizing a circuit that happened to be right next to his compass, he noticed that the needle of the compass deflected. And so his discovery initially was that a magnetic field was created at 90 degrees or at right angles to the current flow. So if this was his compass here, the north needle is pointing in this fashion, the current is flowing in that direction. Those are 90 degrees to one another. And he got very, very interested in this relationship and devoted quite a bit of time to studying it. So he, in his studies, found four basic principles that we're going to look at here. Number one is the magnetic fields that was created was actually circles that were around the conductor. So this is a picture of a piece of paper with a conductor poked through it. It has current, and someone shook iron filings on the paper, and you can see these circular fields being shown by the iron filings there. He also discovered that these magnetic field lines are perpendicular to the wire. So very similar to what we talked about on the previous slide, the plane that you're piercing here with the conductor needed to be at 90 degrees to get the whole circle. If it was at 45 degrees, you'd be bisecting those circles and cutting through multiple planes. So again, the relationship between the current and the magnetic field were 90 degrees. This was very interesting. He found that the direction of current had an effect on the magnetic field because the magnetic field is rotating around the wire, and when he adjusted the current from one direction to another, it had an effect on that rotating field. So this portion here would be a conductor that is coming out of the screen at you, and the plus sign indicates that current is coming out of the screen at you, much like current would come out of the positive terminal of a battery. We're talking about conventional current flow here. And if that is the case, the field would rotate in that direction. But if you reversed it, and the current was no longer coming out of the screen but going into the screen, the magnetic field would then be rotating in the opposite direction. So very, very interesting finding, and we'll be able to put that to use here in just a minute. And then the strength of the field was directly proportional to how strong the current was in the wire. So if you had a 1 amp current flow in a wire, it put out a magnetic field of a certain strength. But if you increased it to 2 amps, the magnetic field increased. So the farther away you got from that conductor, you could still see the presence of that magnetic field. And then the last thing that he discovered is the closer you got to the wire, the stronger the magnetic field. So this illustration does a good job of showing this ring that is closer to the conductor is fatter, showing that the magnetic force there is stronger than it is out here on the perimeter, where you're on the outskirts of where the magnetic field exists. It's going to be weaker in that location. So we're back to our conductor, and we need to determine a way to figure out the rotation and the direction of the rotation. So we have a rule called the right-hand grip rule, and it is very important that you don't get this confused with the Fleming's right-hand rule. And it is confusing when you get on the internet and you do some searches. People refer to them both as the right-hand rule. What I'm describing to you now, is the right-hand grip rule. And there's actually two ways to apply it. This is the first way. So it's just very important that we remember that this is the right-hand grip rule and not the right-hand rule or Fleming's right-hand rule. But if you hold your thumb in the direction of current flow, and again, we're talking conventional current flow, with your right hand, it's important that you use your right hand. The index finger, or the fingers of your hand, will wrap around the wire in the direction of rotation of the magnetic field. So here, the illustration is showing the current flow in this direction right here. And the fingers are wrapping around the wire in a counterclockwise fashion as long as I'm looking down this direction. So the magnetic field lines are going to be rotating around in this direction. So I created this illustration to show it's not just a ring, it's a rotating ring of magnetic field lines. So it is constantly rotating around, and it is all along the wire here. It's not just at a static position. It is all up and down this wire. That rotating field that we have can be used to penetrate other conductive materials. So in this case, I have a soft iron core, and I have this wire that has the rotating magnetic field coming around it, and that magnetic field is actually going to pass through that soft iron core. And we do this for the express purposes of creating a concentrated magnetic field or an electromagnet. We're going to look at that in just a moment. So here is my electromagnet. This is the soft iron core in the middle here, and then I have wrapped it with a very thin wire that's enamel coated. Some people call it motor winding wire, or some people call it magnetic wire. When we get to the bench demo, you'll see exactly what I'm talking about here. But for this purpose, it's just wrapped around that soft iron core, and we are going to try to concentrate the magnetic field lines in that core to make an electromagnet. This is going to be a DC electromagnet. That's why I show a battery here. And we have the positive going to this side and the negative going to that side. So I will have current flowing in this direction. And if I apply my right-hand grip rule, my thumb would be pointed in this direction, and I would have magnetic lines, field lines, rotating around in this direction. Okay, now we're looking at a cutaway of that electromagnet that I had in the previous slide. So this is my soft iron core that's exposed, and these are the cutoffs of all of the wires. So we're just doing this for the purpose of examining what's going on in these individual wires here. So if I zoom in and I look at the wire, this is just one single wire. Of course, there's going to be a whole row of them there, but just looking at the first wire, the wire is wrapped around and it goes behind and comes out right there. So that's why I'm showing a plus sign here. Current would be coming out of this wire, just much like current comes out of the positive terminal of a battery. And if we apply our right-hand grip rule, our thumb would be pointing out because our current is coming out, and our magnetic field lines would be rotating in a counterclockwise direction. So there is my magnetic fields, and you can see this is depicting this soft iron core here, that they are penetrating inside that core, and that's going to have an effect when you group all these together. It's going to kind of concentrate that, but we'll look at that in a minute. And then on the top here, this is showing one of these wires, and I have current going into that wire. That's why I'm showing a minus sign there, because current returns to the negative terminal of a battery. And if you point your thumb into the screen, if you notice, your fingers will be rotated in a clockwise direction. So that is why I show a animation here of the rotating field in a clockwise fashion. So if I have clockwise here on the top of this bar, and it's pushing in this direction, and I have counterclockwise in the bottom, and it's pushing in that direction, it's going to concentrate my magnetic field lines in this direction from right to left, which is going to be useful to us. If you think of a bar magnet has a north pole and a south pole, and the magnetic field lines exit the north pole of a bar magnet and they enter the south pole. And so, keeping that in mind, we have magnetic field lines flowing out in this direction, and they would be rotating around and coming back in this direction. That would make that the north pole of this magnet and the south pole of my magnet. So now if I come back to my my whole magnetic electromagnet here, we're going to apply the second rule of the right-hand grip rule. If I place my hand with the fingers pointed in the direction of the current flow, okay, so we're just kind of reversing what we did before. We're going to point our fingers in the direction of the current flow. The thumb is going to point in the direction that the magnetic field lines are going to be moving. So here I have my fingers pointed in the direction of current flow. Remember, this is the positive, so we're going up, coming around the back. We go up again, come around the back, go up. So that's why I'm pointing my fingers in that direction, because that is the way that the current is rotating. My thumb then, remember this is the right-hand grip rule, so we use our right hand, our right thumb will be pointed in the direction that the magnetic field lines are going to be flowing, which makes that my north pole, because we just learned in the previous slide that the field lines exit the north pole and they enter the south pole. So that is the second application of the right-hand grip rule. Again, it's the right-hand grip rule, not the right-hand rule. So much like the bar magnet, we have created an electromagnet that has these same characteristics that the bar magnet has. The one benefit to this is I can control this by connecting and disconnecting this electrical connection, where on a bar magnet it is constantly flowing those magnetic field lines. So now let's go to the bench and do a little experiment with an electromagnet. So we'll see you over there. Okay, here we are at the bench. We're going to do an experiment to follow up our lesson on electromagnetism. And to do this experiment, I have a heavy-duty lantern battery, 6 volt. I have a couple test leads to make our connections with. I built this electromagnet. This is a soft iron core, and it's about 3 inches long. I wrapped it with electrical tape, and then I wrapped it with this magnetic wire. Some people call it motor winding wire. And I wound it all the way down, all the way back, and all the way down again. So there's 3 layers of magnetic wire on here. And then I just cleaned off the ends of the magnetic wire to make good electrical connections. This red coating is actually insulation. It's very thin. It didn't take much to clean it off, but to make my electrical connections, I needed to sand those ends off. I have a bin here of something magnetic. This happens to be sewing needles, but you could use paper clips if you want. And I have a volt ohm meter that we're going to use at the end of the experiment. And then I have just a standard compass. So I'm going to go ahead and make my connections here. I'm going to connect the black lead to the negative terminal and then connect that to my electromagnet. And I am going to connect the red lead to the positive terminal of the battery and connect that to my electromagnet, and we are now magnetic. And if I break the connection, I lose my magnetism, obviously. And both ends are magnetic, so this end or this end will both attract something magnetic. And I am going to, let's do a pole test here. So before we do a pole test, let's predict what it's going to be, okay? So I have current flowing in this direction, okay? This is my positive lead and this is my negative lead, okay? So I want to use my right hand rule and I want to shape my fingers in the direction that current is flowing. So that would be in this direction here, and my thumb will be pointing to the North Pole. So this should be the North Pole, which should mean what as far as the compass is? Remember, dissimilar poles are attracted to another, or in other words, opposites attracted. So when I bring this up, see how the South Pole of my compass is attracted to the North Pole of the magnet? And if I come to the other end, I should get my North Pole, my North pin, facing the South Pole of my electromagnet. So let's test the theory about current direction and polarity. So I'm just going to swap end for end here, my two ends, okay? So now I have current flowing this direction, wrapping around my electromagnet and going in that direction. So if I use my right hand, again, wrapping the way that the current is flowing, this should now be the North Pole, which means the South Pole of my compass should be attracted to it, okay? And if I come around here, the North Pole of my compass will be attracted to the South Pole of my electromagnet. I'm going to go ahead and disconnect this because this is getting quite warm. And let's see why this is getting so warm. I'm going to go ahead and disconnect this so we don't short out the battery. Here I have a volt ohm meter, and I'm going to set it up for ohms. And let's ohm out this wire here. See what kind of resistance we have. Okay, we only have 1 ohm of total resistance. This is wire. It's thin wire, so it does produce some resistance. But from our Ohm's law lesson, we know that we have 6 volts from our battery, and we have 1 ohm of resistance. To calculate the current, I equals E over R, or volts over ohms. So if I take my 6 volts and I divide it by my 1 ohm, that's going to be 6 amps. So this little 24 gauge wire had 6 amps running through it. It doesn't take long for this to get quite warm. Now the battery actually is still fine. That's why I selected a heavy duty battery. But it wouldn't take very long to actually discharge this battery. So in the conclusions, we'll talk about the reasons why a DC electromagnet may not be our best solution, and will lead us to impedance and using an AC electromagnet. But so now we're going to head to our conclusions, and I'll see you over there in just a minute. Okay, I wanted to go over a few concepts that we talked about at the bench demo, just to make sure that we understand them. So if I take a DC electromagnet and I reverse the polarity on it, does that have an effect on the polarity of the electromagnet? Yes, it does. If we use our right-hand grip rule and we change the current, we're actually going to rotate our hand because our current will be going in a different direction. So that does have an effect on polarity. Okay, so if I have an electromagnet that is wound counterclockwise, I keep the polarity the same as far as my DC source, but I rewind it clockwise. Is that going to have an effect on the magnetic polarity? Yes, it is. Because, again, our right-hand grip rule, we were wrapping our fingers around in the direction of current flow, and we've rewound it, so we're going to have to rotate our hand again. So that does have an effect on polarity. Okay, the iron core that is in the middle, if I pull that out and I swap it and put it back in, does that have an effect on polarity? No, it does not. This is what is being acted upon by the electromagnetic field around the wire. So it has no effect on polarity. Just wanted to go over that just so we understand. Now this is the end of part one, which focused on a DC electromagnet. Now we are going to look into an AC electromagnet. But before we do, I want us to go over a lesson on AC alternating current, and then a lesson on impedance. Those are important concepts to understand before we go into an AC electromagnet. So look for those lessons in the future. We'll see you then.